All right. Welcome, everybody. My name is James Alexander. This is Chalice, Zappa, Serverless OMI. I work for Leaf Software Solutions. I have the slides and the rendered version already available through GitHub pages here. So I think I do have one or two links that I've modified since I published these the first time. So I will have an update to do right after this talk finishes, but those are all available. I've got code samples up in this repository as well. They're named with the appropriate library framework that is the topic that matters, so Chalice, and there's a Zappa folder and so forth. For any serverless talk, we need to make sure we all know what we're talking about. In this case, I'm saying serverless is, there always is going to be some kind of server somewhere. It's just really someone else's in our case. And as a serverless architecture, we're focusing more on our application code rather than how the code is running. So we care more about our text boxes over data or our CRUD app or any of the details of the business logic, and not so much about how the web server is connecting to a processing server that's connecting to a database server. The serverless notion and most of these function as a service or cloud providers allow for scale out possibilities to cloud scale factors. And a big component of it is only paying for exactly the resources you're using. So rather than paying for 24/7 server compute usage, if you only get 3 requests that day, you pay for the compute time that took to service those 3 requests. Kind of a divergence from the actual specifics of serverless, I have a couple of tools that I want to talk about that I want to call out specifically that make my time when working with a serverless project much easier. Most of this talk is AWS centric. I might mention Azure a little bit because I do have an Azure client that I do some serverless work for, and DevOps in general, but most of these are AWS centric tools. In this case, this one's called Assume. So if you are a consultant like me, or if you have more than one AWS account, chances are you are trying to task switch among the various accounts, the AWS accounts. And if you have both of these configured on your local laptop or your machine, and they're named from whatever they are, like in this case, client account, you can have client account 1. I'll have an account for just the Leaf AWS account. I have my personal Leaf. I have my personal AWS account. And so I can assume, and I can enter my 2-factor authentication code directly in a terminal window. And then I have access to my AWS account or the AWS account that I've just assumed. And I check this with a quick like AWS S3 CLI, S3 LS command to make sure that I actually made it into the target account. Another tool that I commonly use on most of these deployments is a tool called Chamber. Chamber is a way of abstracting environment variables, and I can store environment variables in the AWS parameter store rather than in a local .env file or some other measure where I'm just storing it in memory only. There are several advantages where across our dev team, we can share the exact same dev environment variables so that if one of them changes, our lead only is the only one that has to update the environment variable, and the entire team gets to benefit from it the next time they execute Chamber. Now, my dev that I've got mentioned here, it's really just whatever label you want to call it. In our case, we've got 3 environments for dev, demo, and prod. And so in this case, dev represents our development environment for serverless. Chamber is, it assumes basic whatever your current AWS CLI context is. So if you do assume from your base account, you're going to have the Chamber variables that exist in the AWS parameter store of that root account. If you assume some other account, like your client's account or a sub account, you're going to get the parameter store from that account instead. So oftentimes, my assume credential will time out, and this Chamber command will fail because I no longer have a parameter store variable on my base, my root account. So then I have to remember, okay, I have to go back and change assume to reassume back to my client's account. Here are some helpful aliases. These aren't part of the actual command line, but from going from dev to demo to prod, I don't want to type out exec dev each time. The double dash here is an escape so that all future parameter arguments after this point are specific to the next command or not passed to the chamber command anymore. So we combine it here. This is a little bit of a preview for what we can do with serverless. We have the serverless alias SLS here. So I'm deploying, I'm saying on my dev environment, deploy and then -f. So I'm deploying a specific function. And then this alias assumes that the next thing I'm going to type is the name of a function that I previously deployed with the serverless framework. Similarly, if I want to do logs, I can say SLS log start time. So it's really helpful for having some bash food to go along with some of these other tools. Of course, I've already made the assumption that we're all familiar with AWS and the AWS CLI tools, so I want to make sure I call it out and say that, you know, we're going to have to interact with the AWS CLI, and I assume that we've got a secret key and your account key available at some level, ideally through this assume, or there are other tools like I think lpassenv is one that I've seen Calvin talk about before that allows you to inject your secret key from other secret store rather than having it natively on your laptop. Of course, Python, we're going to have virtualenv and pipenv. The slides for this deck are installed using pipenv, which is just a wrapper around virtualenv. Those that aren't familiar, virtualenv is a way of abstracting Python application level dependencies from one app to another so that you can containerize, for using the wrong term, so you can compartmentalize applications 1 dependencies from applications 2 dependencies from a completely separate path on your machine, which makes developing more than one application really, really helpful. Let's get into Chalice. Chalice is the first of my serverless frameworks I'm going to talk about, and it's a nice getting started tool. The kind of overview is if you were writing a Flask app in Python, but you're targeting AWS Lambda, is kind of a high-level abstraction for it. The docs are okay. They're a little bit out of date, I think. I noticed a couple of errors when I was preparing this talk, but I think you still get the rough idea. I have an example of the Hello World Chalice app in this repository that I've linked to at the beginning here. So you're welcome to go and try that. To get you started, it's a pip install, which is nice. There's no extra other binary dependencies from brew install or anything like that. Then that creates a Chalice command line app for us that we can begin a new project. There are other apps for other commands in here for updating and checking logs and so forth. And then it's nice that the entire Hello World app of a Chalice app fits on a single slide when the single slide has a large font size like this. Like I said, it looks very much like a copy paste of a Flask app, but instead of Flask, you've got Chalice sitting here instead. The root syntax or route syntax looks a little bit different from Flask if you're doing path parameters. I have an example in the repository. Instead of angle bracket parens, you have curly bracket parens for adding path parameters in here. Once you've got your app complete, or at least to a point where you're ready to deploy it, you give it a Chalice deploy command, and then after some haranguing, you get kind of this license plate looking API URL that will then function as an HTTP endpoint. So Chalice did all the work there of abstracting API gateway, setting up and sending up the application package, and creating that for us. One big benefit of Chalice is that you also get a local command. So if you want to debug something before you push it up to any of your environments, you can run something locally, have the benefit of your step debugger locally, PDB, any of these things that you want to run. You can change the port that you're running this on with a dash port argument to that. And that gives you benefits that you don't have in some of the other serverless frameworks. Third-party dependencies are either a pip install away from a requirements.txt file, or if you've got other binary dependencies that are not pip installable or do not have AWS Lambda binary compatible versions, you need to put them in the vendor folder, which is one of the downsides of Chalice here, that we need to make sure that whatever we stick in the vendor folder can actually run on an AWS Lambda image. There's a very specific AWS AMI image that is got very specific binary compatibilities. So tools like Docker make building binary packages much easier and sticking those into this vendor folder. But it's still an extra step that you have to go through that Chalice does not provide for you automatically. If you're done with your package, or if you're done with your deployment, you can delete it and delete the specific stage, and then that gets rid of everything that it generated upfront. I've kind of already touched on some of these things. It's very quick and easy to get started. Relatively low code compared to other frameworks. There's no like getting the right zip package format and then uploading it to the console like we used to have to do in the bad old days, 2 years ago. Very little boilerplate. The big downside here for me is that it only works on AWS. And of course, the vendor specific thing, although it's not a Chalice unique con that we can talk about later on. Yeah, to my knowledge, Chalice only works on AWS, and that's kind of a big downside unless all of your infrastructure is on AWS. Moving over to Zappa, I feel like unless there's a licensing problem, they should have had like a Frank Zappa thing here. But every time I try and Google more information about Zappa, I get Frank Zappa stuff instead of the Python Zappa. But there are worse problems to have in the world. One of the big benefits of using a Zappa-based deployment package is that it abstracts the entire WSGI layer of the Python application and converts that to API gateway calls, to the serverless backend. So Zappa, the package itself, inspects your local project, tries to find where your app is, how it's structured, what type it is, and then creates the equivalent API gateway commands in AWS that will mimic the same thing that you've got running locally. So a great use case for Zappa would be if you have an existing Flask app, if you have an existing Django, Bottle, I believe even Cherry Pie or Pyramid, even though I'm not sure that specifically, anything that implements the WSGI layer should theoretically be Zappa deployable. The big piece is you have to tell Zappa where your WSGI app is. But once you get that information, Zappa can abstract away all the other routes and deploy a package into AWS for you. I've got a little demo here that I'll just kind of let run and we can watch. Again, it's nice when these frameworks are so minimalistic and so tiny that the entire app can fit inside of a single slide. And in this case, the running demo also deploys with inside a GIF. So you can see here that coming from a basic virtual env, we've got an app file, the configuration, and see my app here was where the app function is, and then we get a parameter depth, and we've already deployed all the way up to AWS API gateway into a live environment that can be hit by the external world. You don't necessarily have to use a local virtual env here. You could use pipenv, really anything that is a virtual environment. So you don't have to use a VM at this framework level. Zappa inspects the virtual environment that is running in to decide what dependencies should be deployed. And Zappa itself has a list of binary compatible packages that can be deployed. So I don't have a full laundry list, they're all on GitHub, but things like the Postgres, MySQL, Pandas, a lot of these, like SciPy, a lot of these binary packages that I most commonly want to use are already packaged up by the Zappa developer. And as I inherit those as my virtual env, they can be deployed as part of my Zappa deployment process, which is really nifty. Expanding on the Zappa config file format here, instead of just doing a simple web request like we saw with Chalice or with the base Flask app option, if you wanted to configure something to run every minute or on a cron schedule, you specify an event as part of your Zappa JSON config, give it a function, wherever the path to that is here, and the rate at which you want. It can be a cron expression here again as well. And then once you've got that configured, you say schedule production, and it's off to the races. To summarize Zappa a little bit, it is not tied to AWS specifically. And here I don't mean that you can deploy the same thing to Azure. Zappa itself is targeted at deploying to AWS. What I mean that is it abstracts away the WSGI layer. So I have a Python app already. It's WSGI based. I can deploy it already to Heroku, to Python Anywhere, to my own servers. Zappa enables me to pick it up and then push it over to AWS. That's kind of what I meant by that nut tied to it, versus Chalice is specifically designed to deploy to AWS, and it can't be hosted anywhere but AWS or your local machine. I mentioned the con here about the slim handler size settings. I've run into some issues when, I very naively said, okay, it can do any Django project, right? So I took in my entire Django project, pointed Zappa at it and said, all right, deploy the whole dang thing. And it turns out that when you put static assets in there, like your images, all of your HTML pages, all of your CSS, the size of that application exceeds, the base Lambda, obviously, and then even exceeds what the slim handler, the Lambda handler that gets created by Zappa, when that goes and fetches the S3 bucket of the larger 50 meg package. There was at least a bug last time I tried this that would truncate parts of that file, and I wouldn't get the entire Python package deployed. Of the 3 projects that I'm talking about today, this is the only one that does not have a full-time corporation backing it. The original developer is part of a freelance development organization, so they do have their own income coming in that is not part of this project. There's a Patreon page for it. So if you're part of a corporation that expects to have a certain level of service, or is at all squeaky about having open source, that could be a big downside for you if you're considering Zappa for any of your hosting needs. Let's talk about Serverless Framework. The one that kind of, I don't want to say ruins the name of serverless, but makes it confusing when we talk about serverless, because are we saying serverless the framework? Are we saying serverless the architecture? Are we saying serverless a mindset? So from going forward, I'm going to say serverless as a framework. This one is, I'm going to say, much more enterprisey. There is a backend corporation that maintains and charges for ongoing support and help requests and so forth and so on. The package itself is an NPM package, so it's Node.js. It is not Python natively. Originally, the framework was targeting deploying Node.js to any cloud provider. So not just AWS, but it can also deploy to Microsoft Azure, it can deploy to Google Cloud, it can deploy to IBM OpenShift, it can deploy to Kubeless. So they have hit most of the checkboxes. And not just Python, and not just Node.js now. They've also got Go, PHP, Java, Swift, even as languages that you can deploy to these cloud providers, assuming the cloud provider supports that language natively. Like I said, it's an NPM package, so it's an NPM install and not a pip install, which makes me a little bit squeaky, because now I have not just my Python dependencies, but I also have my Node.js, I have my NPM dependency, just to make sure it's correct on my machine and all my developers' machines. But, if I'm doing any kind of client-side programming, or I've also got a React.js app, that's going to be node dependent anyway. You create a serverless project with serverless create, serverless deploy. Obviously skipping a bunch of steps here in the middle. There's a YAML file that has to be configured that gets created as part of this here. There's an example of one in the GitHub repository that goes along with this talk. And very similar to the other 2 projects, you get a license plate look on URL that comes out of the deployment itself. Unlike Chalice or Zappa, serverless is really designed as a project as a unit of work. And as such, it's not tied to having just a single project. I mean, I suppose you could have multiple Chalice projects and multiple Zappa projects too, but it seems almost by design that you can break up, I'm going to call these microservices. So if you've got a user's posts and comments microservice with their own independent data storage mechanisms, their own independent queuing or message brokers, message buses, they could all be different serverless projects that are maintained separately. In our case, for our specific project, we ran into an issue where we were running a single serverless project. However, serverless uses something called CloudFormation when deploying to AWS. All of our cloud deployments are targeting AWS. And when serverless was using CloudFormation, it would hit the 250 object limit. So once we got to a point where we had enough API calls, enough API gateway initializations, S3 buckets, SQS calls, and so forth and so on, that 250 limit got hit. And so then we started to do this to our project, where we would break it up and have the same API behind multiple different serverless projects in the back end. So it was a way to continue using our same serverless framework and serverless infrastructure and architecture, but have different projects that are broke up among these. The one big headache that I'm running into now, however, though, is that when I want to go to the YAML file, like the serverless YAML file, and I do like a command P in VS Code or any of these automatic, completion of the file name, it's the exact same file name across all projects. And since I've got the directory open at the top level for all of the API, the editor doesn't know which one I'm trying to go to. So I have to rely on the path to try and find that. So it ends up being kind of a big headache just to find the right serverless project and the right YAML file that I'm trying to look for. Also, in terms of creating a Python project, this ends up creating a very kludgy hierarchy. With Django projects, you kind of expect the top level is where your managed Py project is, and then you can have dependencies underneath of that. If you've got kind of this in and out directory structure, in our case, we've got this symlinking structure. So we'll have a lib folder that's at the same level as users of post, for example, and then symlink it to these other projects, which looks really nasty to me. So it's kind of another downside to having this serverless, framework structure. The other side of that, though, is that you can take the same Python code and then start deploying it somewhere else, or just restructure it. But there are other ways to break up a project. There are plugins for serverless that allow you to use things like CloudFormation stacks. So instead of having a single CloudFormation stack that's got the 250 object limit, you can have one CloudFormation template reference another one that could then hierarchically define all of the objects that have to be deployed. So that's a way that you could, instead of having a single serverless project, break it up and get a benefit of more than just a single 250 object limit. Breaking into one of these YAML files, you can specify, like here, my service would end up being everything after the main path of your URL. Specify your cloud provider of choice and then the runtime. This mostly comes out when you do serverless create. There are starter templates. You get a Node.js template, a Python template, templates for all the various languages, and you get different ones for different versions of that. So there's a Python 2 and a Python 3 template one. You come in and specify your functions that you want to define. And as a convention, the documentation always says handler. And so by a lot of conventions, I've seen it on the examples, you name your Python code handler.py and then create a function inside it called hello. With multiple functions and multiple handlers, you get the same problem that we had with the serverless YAMLs themselves, where you end up with directories and directories full of handler.py files. So it's difficult to identify which handler.py you're trying to pull out. So when you're defining functions, you want to consider, do you really need it to be called handler.py, or can you just call this, hello.py? Think about the structure where you can categorize your top level handlers and not have to have handler.pys scattered throughout your projects. This is kind of how that looks on the other side for the actual handler.py code. Like I said, you probably don't want to call it handler.py unless you're using a very tiny app and you've really got just the one handler.py. The event and context here are parameters that are passed to us by AWS Lambda. So it gets a little confusing if you want to pull out path parameters or query string parameters. The body itself is a different, it looks like a dictionary. The context holds things like what called us. So in the case of an HTTP API, the context would include information about the refer URL and the headers and other HTTP context. But the context could also come from an SNS message or an SQS queue event firing, all in the case of AWS. So that's what the context object is going to include. So if your function is context dependent, you're going to look into that object for those specifics. So one of the big benefits of using serverless is that it's very, very flexible. It can be deployed to any cloud provider, and a lot more cloud providers than I've used personally. it supports multiple languages, and once you've deployed your whole project, you can say, instead of redeploying the whole project like you do in Chalice and Zappa, you can say just deploy a single function, because I'm only modifying just the one function. And so that gives you a granular microservices level of deploying packages and your whole app architecture that you don't have any other two options. There is a pretty rich feature and plugin ecosystem that you can submit your own plugins. There's a library of plugins already available for it. So if you want to do things like use the CloudFormation stack templates, where you can have more than the 250 object limit, you can use that plugin. And there's many other ones that help with other nuances of the deployment pipeline there. It's unfortunate that my browser window isn't scrolling down to get the other cons, but we kind of get the idea. The local development is not currently possible with the base version of serverless. There is a plugin available for it. Like I said, it's a pretty rich ecosystem, so I don't know all the ins and outs of all the possible plugins, but theoretically this could be enabled so that I think this one by default is for Node.js, and so we would need some kind of a mapping layer if we were going to use it for Python code specifically. And then down here, the one that I can barely read is the, I mentioned before, of organizing a Python project in the scope of this serverless project, where we've got 30 plus projects scaled out wide over a serverless architecture, and it's difficult to map base libraries from Python and get those all mapped together again. So let me go into kind of specifics on on the project that I work on how that all is put together. So this is more general in terms of how you would build a serverless application, not specific to any one of these frameworks. So in our case, this is our app is built using Serverless Framework. So you can consider that the context, and these are all the AWS artifacts that are managed for us by virtue of standing up one of these YAML files that defines all the specifics. So as a user of the site, I will hit some website and I need to log in or connect to the website with either a post or GET, or in our case, a patch for our web API. So Route 53 is connecting to our CloudFront CDN service that, again, is mostly managed by, well, not serverless. We've got a separate piece for our UI, which is all in React.js, and then we automate the AWS CLI to say, here is a list of artifacts that we want to manage in CloudFront. So that becomes our entire React.js app that manages that from CloudFront. At the API gateway layer here, that's when serverless kicks in, deploys all of the relevant HTTP APIs and the mappings to Python code and Python lambdas. Our lambdas are defined all in Python, and those get deployed as part of the deployment package by virtue of using our chamber exec, dev, or demo, or prod in our case. Demo effectively is our staging environment. The lambda itself actually has the list of all the environment variables that lambda is going to reference, things like database connection strings and API keys and so forth that are part of the lambda at that point. And then, of course, our application is referencing a MySQL database that connects to it for queries and so forth. There's a lot of times where a particular task will take longer than what we want the length of a web request to take. And so a web request will come in from one particular lambda, it will stick a message on an SQS queue, and then that SQS queue has a listener of some other lambda that is also deployed by serverless. So serverless can trigger not just on HTTP requests, but on SQS events, like I mentioned here. So both of these sides of this SQS are a separate serverless deployment. And so it could be either a single YAML file with different functions defined, or they could be different projects. And really, the sky's the limit here on the level of complexity. We have a particular processing lambda that some of them do exactly one task, like send an email. We have other tasks that are a task wrapper themselves. So based on the particular JSON that we're handing in, we say it is this task, and here is your other API information or your key information. And then that handler could go and start spawning other things and start feeding back into SQS. And so they'll lead either to most likely different queues, or we've got one task queue that will make a decision based on what it is. Like, is it creating more jobs, or is it processing the leaf of a job that is doing a single record at a time? For example, we have a matching task that has to match a lot of job seekers to a lot of jobs, which is a many Cartesian product problem. And so we're comparing features of each job seeker to features of each job, defining where all the matches are. And each one of these could take a while, a while being a few seconds. And we don't want any one Lambda to try and do all this work. And so we'll do a match per seeker and a match per job. And then a match is the task that would come into an SQS event. And then we allow Lambda to scale out to process all these things. The bottleneck obviously becomes then we need to store all these things in MySQL. So that becomes one of the biggest hurdles of managing MySQL connection strings, connections to the database, and not overloading our database with any one match task. Another common problem that we're going to need to solve is how do we get reports to our users? In general, a lot of our reports are not time sensitive, where they have to be up to the second at the moment the user clicked on it. And a lot of them take longer than a couple of seconds to run, maybe 10, 15 seconds. Our database is pretty small considering the relative scale out potential that you could use with a serverless architecture. But we use, again, this is all deployed from serverless, but it creates a CloudWatch cron-based trigger. And so the cron trigger knows how to call a Lambda. Again, this is all configured by serverless for us. We specify a cron expression that calls into a Lambda, and then the Lambda does whatever it's supposed to do to generate a CSV file. We store that CSV into an S3 bucket that we've defined as a public bucket, but the creation of a new object is not necessarily public via that public S3 unless you've turned on web hosting for it. The way we handle these requests for the reports is that as the browser requests the URL for the object, the report, we generate, when we render the server render the page for that client, we hand them a one-time use S3 URL. So we create these report URLs that are good for 1 hour by default. That gets rendered as part of the page. So the user clicks on this S3 link directly, and then that S3 link knows how to return a bucket and a key that we've predefined for that key length. When our reports are generated, we generate them and stick them over the exact same key that we had before. And so that way, when our later process says, give me a report for report X is the same name as what it was before. And so we can generate a key based on the same, we can generate a new link based on the same key in that bucket. So some gotchas, not just with serverless framework, but with serverless architectures in general. You've still got to store data somehow. In our case, we're using a relational database model that's stored in RDS, and that very much is our bottleneck. If things were to scale up dramatically now, MySQL would be the bottleneck for sure. You'd have to think seriously on how much scale you're going to need. So if you want to do large scale out immediately, you want to consider a DynamoDB or Azure Cosmos DB, Google table for cloud native storage of these resources. Then you've got to consider the costs of IOPS on each of those resources, which are throttled by that instead of by raw compute time. So I mentioned the scale out of server compute increases the MySQL connections here. This was more a problem in our specific project. We had a bug in our Python code where they made the assumption of, okay, our Lambda is going to fire, takes our Python code, runs it, and then the Lambda goes away. However, we were finding that the Lambda would stay around for a while and be reused. And each new request to the same Lambda would create a new connection to the database. And because our code had a bug in it that would not clean up those connections properly, we would easily fill up our MySQL connection count. So clearly that was our fault that we're not using context managers to close out our connections correctly or doing .closes on our SQL Alchemy sessions. But just know that as a Lambda is invoked, it doesn't necessarily mean that the Lambda goes away immediately. And also, similarly, if you get a lot of requests horizontally, AWS will create additional Lambdas that will all try and do the same thing. And so you could have, by normal usage of the code, max out your MySQL connections, which again is causing the bottleneck. So if you were to run into that situation, we don't have anywhere near that traffic today, but that's something else to consider if you've got a lot of horizontal traffic that are all going to have a single choke point back to the MySQL database. In the case of our serverless architecture, serverless framework, you get those license plate looking random URLs instead of something that's, myapp.com or whatever. You can use Route 53 and API Gateway to map those all together. In our case, we're using something called base path mapping of API Gateway. So we've got, in our case, the Lambda side of things is all an API, an HTTP API. So it's api.myapp.com, for example. And then for each of our serverless projects, everything after the slash, for example, myapp.api.com/users/project/whatever, all of those slashes are different serverless projects. And so those all need to be mapped up into the same domain name, which is a big gotcha when you add a new serverless project or you add new functions. Those are not automatically added unless you write a script that goes through and compares all of your serverless projects to all of your API gateway projects and make sure that you've got the base paths mapped together for each of your environments. So that ends up being a big headache. And I've already mentioned this a couple of times, trying to find the right serverless YAML when you want it is a big pain for our modern tooling. So that kind of wraps up my talk. I'm happy to answer any other questions. In general, I think that serverless computing is probably a wave of where we're going to go for most application development, but today there's still a lot of headaches, but these tools in general make deploying these things much, much easier than wrapping up your own zip file, creating your own vendor default repository, getting the right binaries for just the right time. Unless there's other questions, that's all I have. Thank you very much.
Thanks, James. That was excellent. I did think of one question inspired by the top line of your previous slide, which is MySQL still the bottleneck.
Right.
Would Aurora serverless, the special magic AWS MySQL service that can scale?
Yeah, it's a great example, a great possibility.
Is that an answer? Yeah,
it is an answer, and it's definitely a possibility. So since we're running ours in RDS, it definitely is our primary bottleneck at this point. So the problem is that the base level of Aurora is an order of magnitude more expensive than what we're paying for our relatively mid-level of RDS. So you really need to have that as your problem. So I was just more identifying it here as if you're writing something serverless by default, it's cloud native in that sense, but standard MySQL is not necessarily cloud native by default. So you need to go with the cloud native RDS instance, relational database instance, like the AWS Aurora, like you mentioned. So.
Cool, thanks. Okay, if you're done, I don't see any more questions in this. Oh wait, there might be a question. There's a post. No, that's just Calvin. Post and posts.
Sure.
Oh, here's a question.
Yeah, Calvin.
Have you from Josh Vernon in the Zoom Q&A? Have you ran into issues where Lambda is costing much more than you thought it would?
That's a great question. I looked at our cost logs before this talk. I think it was a couple of weeks ago, and the notion of it costs less was in my head, thinking, okay, if I'm running this on Heroku or Python Anywhere, I can spend probably on the order of $50, $100 for 24/7 uptime, and our Lambda cost is closer to $300, and then our RDS cost is about that again. So it is surprising how much that actually costs. So that's a really difficult question to answer ahead of time, though, too, because we've architected our app specifically to work this way. So the whole queuing of functions to run off an SQS queue and scaling out that performance so that you don't have any one function that runs for an hour like you could do in a Heroku Celery app or something like that. It's just an entirely different architectural pattern. And it's difficult to estimate that ahead of time. So yeah, I'm a little bit surprised by how much it actually does cost. So, and my line for those types of questions now is, cloud, it doesn't necessarily mean it'll cost less, but what you're paying for is the flexibility of doing more and doing a more variety of things. So it's a trade-off. Like most technology, there's no silver bullet, and you just have to monitor your costs and say if that's too much and too expensive, you have to consider another option.